Welcome to our third talk for today. We present Ján Lieskovský with inspecting security of Docker formatted container images. And let's start.
Hello, my name is Ján Lieskovský. I work as software engineer for Red Hat, and I came here to speak about security of Docker formatted container images, why we care and why you should care too. We first need to set up some basic terms. Docker formatted container images, it's interesting application platform. Docker has been like hype and fashion in recent years. Many people got accustomed to use it, and it looks promising to developers. Just do the reasons they can focus on the content rather than on the build process. They can aggregate the data via the Docker container format specification. There is simplified release management. It's not necessary to take care about how the software or application would be released. Docker provides uniform approach to this. And of course, last but not least, it's easy to customize the content. On the other hand, it's also interesting and promising for the users. Maybe because due to the very same reasons, there is plenty of applications available at the official Docker Hub. Again, it's a question of a simple deployment of the applications. You just pull the image and basically are set up. No need to special difficult installation. This approach or this is also interesting for administrators when it's necessary to update the application. It simplifies the life for them, so they can more easily deploy the updated version. And again, easy customization. In the case the provided content doesn't meet the exact requirements, it's easy to modify it. Some basic terms, so we need to distinguish between Docker image and Docker container. So Docker image is basically some collection of root file system changes. And what's important here is it's read-only image. It doesn't have some specific state. It's basically set of a couple of layers placed one on the top of the other. About the process, how the images are created, basically all of the images are created or derived from the base image and transformed into the final image via a couple of operations that in the terminology of Docker are called transactions. These transactions allow to perform actions like run a command, add file or directory, or specify a process that would be actually launched when the container is started, the image is started. On the other hand, the container is already some instance of the image. Should I use the analogy of object-oriented programming? We can compare it that images are classes and the containers are the actual instances of them. The container contains of the image, the execution environment, and the set of instructions that were used to create the image. It's possible to have many instances, many containers of the very same one image. This picture provides or sheds some light about the actual infrastructure of how Docker works. So there is traditional server to client infrastructure. The client may be the same like the server, like the Docker hosts. We have some Docker registry when the software publishers provide their images. When we can pull the content from the registry, and we will receive an image and run that image via Docker run command. Or the vice versa, we can create the image completely from scratch from a Docker file. So we would use the Docker build command and run the container. On this picture, it's good that it's clear. There is clear distinction between the images and containers. Comparison of containers and virtual machines. It's often believed that containers are something pretty new. It's not that really true. They have been here for a pretty long time. Just Docker productized them, simplified them to wider use. Basically, the difference here is we have some infrastructure hardware, the host operating system. In the Docker image on the right, there is the Docker engine, and the containers consist of the binaries, libraries, and applications. Compared to that, the virtual machine has another layer or different layer. It's a hypervisor, and yet each virtual machine, besides of the application and the libraries, also contains operating system of the running guest. This picture can be interpreted or viewed like Docker is or containers are more effective because there isn't a need for the guest operating system. So it's consumes less resources actually to start the container when compared to the operating to the virtual machine. Container security and wide matters. The security of the Docker containers is based on some very well created features of the Linux kernel, like kernel namespaces. Basically, when we want to speak about security of Docker runtime or container runtime, we need to focus on three basic areas: the security of the kernel, to keep it updated, the support for namespaces and control groups, security of the Docker daemon itself, like it's a service. It also has some attack surface, and we also need to keep it updated. And then last but not least, the security of the concrete specific Docker file. The Linux kernel namespaces provide some form of isolation, like in the concept of virtual machine, you have completely isolated virtual machines. In the concept of containers, this isolation is reached via kernel namespaces. There is own network stack per each container, and the resources like CPU cycles, memory, assignment, input-output bound are managed via control groups. There are also Linux kernel capabilities basically capabilities in traditional Unix world. There were a separation to the user was separated to two roles, like the privileged one, the administrator, and the unprivileged one. Linux kernel capabilities provide more fine-grained distinction to be able to specify more items that reach better distinction of the rules. There are also concepts like hardened kernel and mechanisms like SLLinux and Upper Armor. Why I'm mentioning all this? It might seem boring. Basically, when you look at the design of the way how the container runtime is designed and implemented, it looks reasonable. The issue is that there might be something we aren't aware of. We might overlook something. And as container runtimes accepted more wider audience and got used by more wide groups of customers, there were efforts to inspect the security of the container runtimes. And some of those articles discussed that not each major Linux kernel subsystems can be namespaced. Basically, the Linux namespace is the basic building block of the runtime, and the complaint was not each of the devices, not each of the kernel modules can be namespaced. And what happened, at 9th June 2014, the Docker team announced version 1.0, and the history has shown it has been some strange coincidence of the history that a week after the 1.0 version was released, some guy sent innocent email to open source security mailing list, like saying, hello, I have found this issue. It's in the version of 0.11. And what's actually interesting, I'm not really sure they really fixed the problem. They just told me that they changed something in the capability handling. So what we might overlook is an exploit called Shocker, and it actually demonstrated that if someone forces you to run a Docker image, Docker container, due to some reason, because it's flexible, it's like straightforward, it's very common, this exploit can obtain access to any file on the host operating system. One might say it's okay. It has been like 2 years ago, and it isn't problem like today. And we will return to the same picture. Here, the scheme of the container runtime was like expressed. It's lightweight and it's easy to run the containers. What's happened here is that the virtualization too, it requires more resources. There actually is another level of protection the attacker needs to like overcome when they want to exploit something, and that's actually the guest operating system. They to exploit something, they need to find an issue in the operating in the kernel of the guest operating system, then exploit in the hypervisor, and then they can actually touch the final hosting system. In Docker, you can see that it's a bit more, it's easier because it's not, there is missing the layer. So the result, what like this exploit caused is that the engineers that originally invented and implemented Docker revisited the security features of Docker and provided some recommendations like, okay, it's secure, but you need to follow some good practices, like don't run things as root, drop capabilities, and I don't know, enable SL Linux. Don't use shady SUID binaries. And this is another example, like drop reviewers as quickly as possible and watch your logs. Like we said before, Docker seems appealing because the users see the plenty of applications available. Those applications are available in the official repositories, and also anyone can build their own repository and create, I don't know, I have searched for Mongo, and there are more than 2,000 instances of the repository. The natural question you might ask is who have built these images? Like, how can I trust? Docker listened to these questions or concerns from the users, and in the August 2015 introduced something called Docker Content Trust, and basically it works from this workflow allows the repository content to be assigned. It's performed automatically in the moment when the publisher wants to publish new version. The service encrypts it, signs the content with the private key of the publisher, and on the other hand, when the customer or user receives the content, again the Docker daemon itself verifies the signature of the content, and the pull fails if the identity doesn't match. There are two types of keys in the Docker Content Trust: the tagging key and the so-called offline key. Tagging key is basically required when you are creating new repository, and it's actually intended to be shared with all people that they are expected to cooperate with you on the content. Okay, so looks I can't move. I should stand. And the offline key is something like master key that it's actually used to actions like when you need to revoke the tagging key, and it's intended to be actually kept safe. What the Docker Content Trust can provide for us is we can verify the identity of the publisher. We can trust that the content, the image wasn't changed during the way when we are pulling it from the repository. It also helps to detect like replay attacks. Some attacker would want to pretend he can provide the image for you, but it would be already outdated. And also, like it's possible to detect the key compromise. Okay, so we know who have built these images. The next question might be how these images have been actually created. This is basically the reason I have previously mentioned the slight difference between the images and containers. Each image is basically derived from the base image and transformed into the final form through steps of instructions. We can create new images two ways, like either specify a Docker file and build a new container from it, and or we can update an existing container and commit the changes back. Obvious question might be who can create these images. The issue is that anyone, as it's easy to use, and it should be easy to use, and it should be accessible for everyone. Basically, anyone can create new images. So when we retrieve some remote image, what we actually trust in that moment into, it's basically we trust that the base image, the image we are actually pulling, has been created in a secure way. The changes that have been created on the top of that image have been performed in a secure way. And if there is some security flaw in the base image or in the changes, that the content we actually retrieve has been already updated. So basically, just by pulling the image, we like assume three facts to be already met. Like I think everyone wants a secure container infrastructure, and we can trust the design and the publisher of the image that they are doing their best to provide the container for us. But it's our responsibility to verify that the image is truly secure. The image, the host, hosting the container runtime, and also the daemon. So we get to the point how to inspect or verify that the image we retrieve is actually secure. It needs to be split into two steps, two tasks. One step is to inspect the image for presence of security flaws. This process is called vulnerability assessment. And the second step is to check if the internal configuration of the container is set up in a secure way. This is called security compliance. Maybe some of you have seen security advisories like this. This is example of a security advisory for Firefox, which produced by Red Hat. Here is the equivalent from the Ubuntu distribution. Basically, what's interesting is you can see the list of security flaws that got corrected within this update. This is the HTML form, and the problem is that this form isn't completely right for to be processed when you want to scan containers. So we need something that would be easily consumable for machine processing. Basically, we need a standard, like standard that would allow us to express the information about security falls in some uniform way. We also need the information about security updates to be present in the form of this standard. And the last part is the scanner that would actually perform the scan for us in an automated way. When focusing or inspecting the features the standard should have is that we want to represent the configuration of the systems in some uniform way. When speaking about systems, I mean now like all kinds of systems, like regardless of the platform, regardless if it's like a physical machine or a virtual machine or its container, the standard should be able to represent configuration information of any kind of computer system that can exist. The standard should be able to analyze the system in question for presence of some kind of computer state, like for example, if some patch has been applied or if there is some security vulnerability present, and should be also able to report the results back in some uniform way. So we use a standard which is called Open Vulnerabilities and Assessment Language. Basically, the name speaks about the purpose of the standard. It's able to scan security faults, security vulnerabilities, but also it's able to detect computer state and detect some specific configuration. Before we said we need the standard, we need the security Errata available in the form of the standard and the scanner. The security Errata, basically a lot of vendors in the Linux area producing operating system dedicate a lot of efforts to create security updates information in the form of OVO files. To mention some of these, I will provide. These are actually links, so you can see the concrete locations. But just to mention the most two is it's Red Hat and Ubuntu, but there are more of them. And the last part we need is the scanner to perform the automated inspection for us. And on this place I would like to introduce the OpenScab project, OpenScab Ecosystem. Here's the overview of the tools, not complete overview, but some snippet of it, of the tools we produce. It's the command line interface utility called OpenScab Base or OSCAB. It's mainly intended to be used in shell scripts, playbooks by the administrators. Then there is the graphical interface on top of it called SCAB Workbench. Besides being able to scan the system via graphical tool, it's also able to modify the security policies. I will speak about security policies in a moment. And most recent addition to the ecosystem is OpenScab Daemon. Basically, there is some effort to be able to scan any kind of computer system, like physical, virtual machine, container. There is effort to run the scans on a regular basis, provide some system service that would, for example, scan the system I don't know, each Monday or each Wednesday. And the Scaptimony is actually the database that it's used to store and process the results of the scans. Here's example of what we actually need to do when we want to scan containers against the presence of security flaws. So we install a package. This is example from Federal system, but when you look at the OpenScab portal page, I have link at the end. There are the software is available also on different distributions. So we install the OpenScab containers package. The second command is actually retrieving some randomly chosen container from Docker Hub. We retrieve the overall information about the security flaws. In this case, since the container is based on Red Hat Enterprise Linux 7, we retrieve the overall security flow information for this type of system. We start the image and actually create a container from it. And here is the actual scan. So we call utility which is called OSCAB Docker. And with these arguments, you can see some strange looking identifiers, like I don't know, 2016 something. And basically what matters here is the last column, in the sense that all those lines that have finished with the state of false means that that container isn't prone to some specific security flaw. The situation is worse when the specific advisory was met, when the result was true. In that case, it means that the container is actually vulnerable to some known security flaw that actually got a fix for the issue. Like we said, running untrusted containers might be dangerous. It actually, the Shocker exploit demonstrated that in the moment you actually run the container, it might be able to access any file on your host, on the computer hosting the infrastructure. So it's not a good practice to run untrusted containers. Instead of that, we might want to scan images instead. Like yet before we start the containers, we would inspect them. It's possible too. Basically, it's the same tool, OSCAB Docker. Similar output, like you can see again, there are two instances of pass or true state, meaning that there are the two issues found. Basically, what differs is the actual command that was executed. In the first example, it was the container CVE, and now it's image CVE. We previously mentioned that when we want to inspect the security of containers, we need to focus on two different areas, like inspect the security flaws, the presence of them, but also some containers might be configured in an insecure way, like configured not enough, not strong enough. So the second part is actually verifying if the internal configuration of the data or the services is configured in a strong enough way This is referred in like security area, like security compliance, checking security compliance. So to be able to do that, we need to introduce yet another component into the puzzle, and it's called, in our case, ESCAP Security Guide. It's basically a set of security policies that are already available and that have been already created. And these security policies define some criteria or requirements what a securely configured system would look like. There is a lot of them just because the different use case each computer is intended to be used for. To mention an example, one might expect that some default configuration of the distribution would be secure. It's true just on the halfway, and it's because, of course, the creators of the operating systems tend to use secure protocols, algorithms, and improve the security of the whole system. But due to the way those products are intended to be used, it can be used on physical machine, on virtual machine, in the cloud. It's not possible to create some ultimately secure computer environment. So you basically need different types of security policies, and those security policies would be specific to the concrete application or usage of such a computer system. So here is syntax of the running the tool when we would like to scan an image against the security compliance. We can see it's getting a bit worse. There are more arguments in this case. Basically, what remains the same is the OSCAB Docker and the container itself, the image itself we want to scan. We specify that we want to scan image, like in the previous example. It's also possible to run running container, and all those remaining parameters, XCCDF, eval, and profile. Basically, we specify which profile from the security policy to use, where to store the result of the scan, and actually that long line refers to the specific security policy we want to use. It's a security policy for Red Hat Enterprise Linux 7 in this case. And once the scan finishes and we create that report.html file in the temporary directory, here is example of as a single file scanning that randomly chosen container from GitHub resulted into one or more rules weren't satisfied, and this is example actually of a concrete feature that wasn't met. In this case, it was the container allows to log in computers, log in users that have empty passwords. So it's basically an example what in a which way how the container might be configured insecure. And when performing the scan of the container, all of those failures, all of those issues found would be represented in the same way. In the sense, you would get notified the specific rule, how much urgent or how much important it is, like from the point of security of the system, why it's what it means when we scan the container against this rule, what we are actually checking, and the rationale, what's the motivation behind trying to check this configuration, why it's important to perform that check. And you can see also the remediation script. Remediation script is something scanning a computer or container. When the scanner finds some failures, it's also able to automatically correct them, and the section remediation script actually displays the specific command that would be executed to fix this concrete failing feature. And that's actually it, I think.
Thanks. Yeah, no questions panel. Any questions?
Can I use it with Debian or Ubuntu?
There actually is this way. The scanner is already available in the Debian, but the policies aren't yet. Like the issue is that the policies aren't created for the Debian and the Ubuntu distribution yet. When scanning security faults, they create them automatically, like the CV. It's the process you can download and you can scan any computer virtual machine from Debian or Ubuntu for presence of security flaws. But when you want to check the configuration, those policies weren't created yet. We, like 2 months ago, like merged some effort, some Debian rules, and into SCAB security guide. So there is some, how to say, starting effort to be able to scan also Debian and Ubuntu systems when for what is worthy regarding configuration. But for security faults, you can.
Okay, because I checked Debian on it, and they seem to have published the info since 2001 till 2012, and then because of some changes, their script broke, and it's still broken. And since there's no information from Debian on this, it's kind of unclear how can this be used widely.
That's true for Debian, that the process of producing the overall changes isn't like transparent and isn't working right now. But Ubuntu, like 2 months ago, started a completely separate process. They produce own security data and at a different location and not derived from Debian. If you are interested, I can point you to the, or actually it is, if you visit the link, actually it points to the data, overall data for Ubuntu.
Okay, thanks.
Any further questions? Okay. So far then, thanks again, Ján. And we have the lunch break.
Thank you.